Click the bell icon to get latest videos from Ekeeda.
Hello friends, welcome back to Electromagnetic Field Theory. We are on the last topic of the chapter number 4, Energy and Potential, and the topic name is Energy Density in Electrostatic Field. I hope at this time you are all familiar with the word electrostatic field. We say the static charges produces electric field, hence we call that electrostatic field. Now the title first term is energy density in electrostatic field. As we hear the term energy, we are all well known about the law of conservation of energy. The energy can neither be created nor be destroyed, but it can change from one form to another form. So here in electrostatic field, energy density term we have to get into learning. This topic can also be called as energy stored in the field of system of charges. So how the energy comes to the electrostatic field, what is the behavior of that particular electrostatic field with the term of energy that we are going to see in this topic. So let us start energy density in electrostatic field. In this topic, we are going to derive some simple expressions for energy stored or energy density in electrostatic field. So initially we consider there is no charge in the free space. So if there is no charge into the free space, it means there is no electric field. So there is no role of energy in that electrostatic field in the field. Now we consider by some external source, somehow we manage to get some charges into the free space. The charges we name Q1, Q2, Q3 and Q4. For example, we are taking only the 4 charges. We have managed some external source to carry these charges from some infinity to get into our region under consideration. Now initially there it was no charge, so no electric field. So first of all we have managed to get charge Q1 from infinity to this particular space. So before charge Q1 there was no charge, no electric field, hence no energy will be stored. After charge Q1 we say Q2 has carried. After charge Q2 we have carried Q3 to this region. After charge Q3 we have carried Q4 to this region. So this way we can have n number of charges to form a system of charges producing electric field. So we can say electrostatic field due to a system of charges. Okay. Further, it can be infinite number of charges where we have to consider the differential charge and we have to consider the expression relating to the differential charge giving electric field intensity, energy or energy density. So here as the first charge is Q1, before first charge we consider there is no charge, hence no electric field, hence no energy stored. Energy stored will be equal to 0. After employment of certain electric external source, we have brought this charge Q1 and build this network further. Okay, so definitely a work has to be done as we are carrying the charges from infinity. So for the first charge, as previously there was no charge, so no electric field, we know that energy expended while moving a point charge in the electric field because of certain another source charge. So no source charge was present. So for bringing Q1 from some infinity to this region, energy stored will be equal to 0 as there won't be any work done. Now when we move Q2 charge from some infinity to this region, Q1 is pre-existing. So it means definitely some work has to be done. While we bring Q3 to this region, Q1 and Q2 are already present. So there also the work done will be present. So similarly carrying forward, work done we have to consider. So for work done we know the formula W is equal to minus Q integral B to A E bar dot of dl bar. We can also term it to be the Q into V suffix AB in joules. Here also we can put the unit joules. So this is the work done when we move the point charge having this magnitude Q from initial position B to final position A. So the electric field that was already present, that is to be represented by E bar, and the displacement from B to A we have to represent by the differential length dl bar. So this we can denote with the help of potential difference also, VAB. So while bringing charge Q1 we have considered no electric field, so this equation will not be applicable. When we bring charge Q2 to the region under consideration, that time this electric field is because of the charge Q1. While we bring Q2 to this region, the electric field E bar is present because of initially present charge Q1, and the displacement we have to consider. So this Q will be Q1, will be Q2, and electric field will be of that of the Q1. So work done while bringing charge Q1 will be equal to 0. Hence the energy stored will also be equal to 0. Now work done to the position of Q2. So it will be Q2 multiplied by potential difference V21, because we have simplified the formula of work done to Q into the potential difference VAB in joules. So here for work done for bringing the charge Q2 will be Q2 into V21 joules. Similarly, while we bring charge Q3 in the specified region, so already existing charges are Q1 and Q2. Now we bring Q3, so there are two electric fields already present, one because of the charge Q1 and another because of the charge Q2. So in such a case, the work done to the position of Q3 will be work done to the position of Q3. It will be given by Q3 multiplied by V31 plus V32 in joules. So while the charge Q3 is getting to its position, the potential difference with respect to the first charge and potential difference with respect to the second charge we have to consider. Similarly, work done to the position of Q4 will be given by the magnitude of the charge Q4 multiplied by the potential difference. So the potential differences will be 3. So it will be V41 plus V suffix 42 plus V suffix 43 joules, and so on we have to consider, because at the time of Q4 the 3 charges are existing, so there will be 3 potential differences. At the time of Q3 the 2 charges will be already existing, so we have to consider the 2 potential differences. At the time of Q2 only 1 charge is pre-existing, that is why we have to consider only 1 potential difference. So this process bringing the charges from infinity to the specified region may go on, and hence the total work done we can represent with capital W, or we can say it is the total energy stored in the field of system of charges form. While we bring the charges, we build the system of charges. So here we represent the total energy stored, W, or total work done will be equal to, for the first charge it will be no work done, it will be no energy stored. Hence for the second charge we write the first term Q2 into V21. For the third charge there will be 2 pre-existing charges, hence we write V31 plus V32 in multiplication with Q3. For the fourth charge Q4 we have in multiplication V41, V42 and V43. So this process may go on. Hence we can write W is equal to Q2 V21, Q3 V31 plus Q3 V32 plus Q4 V41 plus Q4 V42 plus Q4 V43 and so on. Let us represent it by equation number 1. Now V21, V31, V32, V41, V42, V43 and so on. These are the potential differences. The potential difference while we bring one charge in the field of another charge. So here changing the order of 1, 2, 3, 1 so that the convenience can be done. The equivalent representation we can do W is equal to Q1 V suffix 1, 2. Okay. Plus the second term will be Q1 V suffix 1, 3 plus Q2 V suffix 2, 3 plus Q1 V suffix 1, 4 plus Q2 V suffix 2, 4 plus Q3 V suffix 3, 4. So the first charge we consider to be when the existing electric field is there. So let us say this is equation number 2. By adding the two equations we can write twice W will be equal to Q1 in bracket V12 plus V13 plus V14 plus and so on plus Q2 in bracket V21, V23, V24 and so on plus for Q3 we can have V31, V32, V34 and so on plus for Q4 and so on. So let us say this is equation number 3. Now in the region specified, for example we have considered 4 charges that are the finite one. So some finite charges if will be there. So at let us say point the position of charge Q3 there will be the potential due to Q1, Q2. At Q4 there will be the potential due to Q1, Q2, Q3. So let us consider V1, V2, V3, V4 and so on are the potentials present at the positions of charges Q1, Q2, Q3 and Q4. Therefore we can represent the equation 2W twice W is equal to Q1 V1, Q2 V2, Q3 V3 plus Q4 V4 and so on. Therefore in generalized form we can write twice W is equal to summation I is equal to 1 to n Qi Vi in terms of joules. Now up to this case the number of charges were finite. If this process goes on in the specified region there may be infinite point charges. So in that case we have to consider the volume charge density denoted by rho v. Rho v is given in coulomb per meter cube. So here we have twice W, the left hand side of the above equation will be given by volume integral rho v into total volume V dV. Let us say this is the next equation. So now utilizing the point form of Gauss's law. The Gauss's law we have in integration form d bar dot of ds bar for the closed surface integral given by volume integral rho v dV or divergence of d bar is equal to rho v dV, rho v in point form also called as differential form. So in this equation in place of rho v we shall be using divergence of d. That is why the equation will get to form twice W will be equal to volume integral in bracket divergence of d bar and the potential V dV. Now we have the vector identity to deal with divergence of d bar and the scalar electric potential. Hence we can write V in bracket divergence of d bar is equal to del bar dot V into d bar minus d bar dot del bar V. So using this vector identity in this equation we can get the above equation as twice W is equal to volume integral in the bracket del bar dot of V d bar dV minus the second term will be volume integral in bracket del bar V dot of capital D bar dV. So we have from one integration term to two integral terms. This has del bar dot of V d bar, this has del bar V dot d bar. Now if we consider the first term of the above equation, so it involves del bar, it involves V, it involves d bar. Hence, as it involves three terms, we have to consider the three parameters for that particular integral. We may better represent it by utilizing the integral form of Gauss's law. So the first term on the right hand side can be written as twice W is equal to closed surface integral V into d bar dot ds bar minus volume integral del bar V dot d bar dV. So here we have used the Gauss's law in integral form. Now it has V, that is electric scalar potential, d bar, that is electric flux density, and ds bar, that is the differential surface area. Now the potential V varies with the distance r as inverse relation. As we go on increasing the distance between the source of electric field and the field point, the potential goes on decreasing. Okay, potential increases as the distance between the field point and the source decreases. Okay, the second thing, that electric flux density has inverse relation with r square. Okay, so this also reduces when r increases, and when r decreases, the electric flux density go on increasing. Similarly, the differential surface, now here the complete surface I show, has relation with the r, the distance separating the source position with the field point position, but it has direct relation, that is directly proportional to r square. As the distance of field point increases, so that time we have to consider a large region having the closed surface, you can say. So this has inverse relation for D and direct relation for R. So here we have the relations of the electric scalar potential with the distance R, the electric flux density with the distance R, and the surface area with the distance R. To consider all the three at one, we have to consider that the first term of this integration reduces equal to 0 when the distance of separation between the source charge and the field point R becomes infinity. Hence, we will be rewriting this expression without this first term. So twice W will be equal to minus volume integral del bar V dot of d bar dV. So del bar V is actually, there is no dot or cross in between. V is electric scalar potential, so it becomes the gradient, that is potential gradient. It is the representation of potential gradient dot product with electric flux density. Now for the potential gradient, we know the relation that E bar is equal to minus grad V or potential gradient. Hence in that equation we shall be substituting, in place of gradient V, we will be using electric field intensity. So minus and the gradient of potential we will be replacing with E bar. Hence we will be writing twice W will be equal to volume integral E bar dot of d bar dV. So here we get the product of electric field intensity vector and electric flux density vector, that are the prominent parameters to measure the electrostatic field. Now we have one more relation relating E bar and d bar, that d bar, that is electric flux density, we obtain when we multiply epsilon 0 with electric field intensity, provided that the medium is free space or air. Now d bar is equal to epsilon 0 times E bar. Hence E bar we can write d bar upon epsilon 0. So we can convert the right hand side of this equation either in electric field intensity vector only or in electric flux density vector only. So while having this substitution, we can write W, that is total work done or the total energy stored in the field of system of charges form, W given by volume integral E bar dot of d bar upon 2 dV, also equivalent to volume integral d square upon twice epsilon 0 dV. So this is the representation in terms of electric flux density only. Now the next representation will be volume integral epsilon 0 capital E square upon 2 dV. So all these three representation holds the SI unit, that is joules. This is the total energy stored in the system of in the field of system of charges. Now if we differentiate any one of this equation, we get the form dW is equal to, let us say the first equation, E bar dot of d bar upon 2, it will be dV. It will be equal to the second form d square upon twice epsilon 0 dV for differential volume equal to epsilon 0 E square upon 2 dV for the third form of this equation. So this equation we are differentiating. W is equal to okay. So we get this form. Now from the differential volume from right hand side, if we take to the left hand side, we can represent dW upon dV is equal to E bar dot of d bar upon 2 is equal to d square upon twice epsilon 0 is equal to epsilon 0 E square upon 2. So this will be given the unit joules per meter cube. As we are taking differential energy stored or differential total work done upon differential volume, for differential volume we have to mention meter cube. So joules per meter cube, we can say this is the energy density. So thus this expression can be the energy density for electrostatic field, and the earlier representation is the total energy stored while we form the system of charges in that particular electric field. So based on to this concept, in the subsequent lecture we will be solving 3 problem statements and will finish up with the 4th chapter, energy and potential. Thank you.